Hello everyone, so welcome to our video lecture. So dear students, welcome back. Let's continue with the stereoisomerism. See, this is one of the most important video lecture I am making. Why? Because here we are dealing with most important topics. See, we have discussed about how to check about optical purity, how to check enantiomers, diastereomers, how to check RS configuration, and all these cases, what are meso compounds, what are chiral center, chiral carbons, and everything. Now it's time to calculate the total number of isomers, and now also specifically it's about a total number of stereoisomers. Okay, see, calculation of this part is very specific. Why? Because it is one of the most important topic which is asked in competition examinations. And even if I use that in JEE mains or advanced in integer type questions, you can see previous year questions. This is one of the favorite topic of JEE examination as well as in NEET or other competitive examinations. Okay, so let's continue. Calculation of total number of stereoisomers. Okay, so here we are calculating total number of stereoisomers, but let me tell you, the question may be asked like total number of isomers. So when you say total number of isomers, it means structural isomers as well as stereoisomers. Okay, so when you are asked structural isomers, what you have to do? First of all, draw all the structures. Okay, now after drawing all the structures, check in one by one. In every structure you have to check whether it can show geometrical isomerism or optical isomerism by checking the number of chiral centers. Okay, so let me define here. See, if you have to check total isomers, first check structural isomers. Draw all structures. Okay, so first of all you have to draw all the structures. Clear? Now in each structure you need to check geometrical isomerism part, means whether it can show cis trans or EZ or syn anti, and then check optical isomerism part, means whether any part of the molecule can show optical activity, means whether it is having chiral center or no chiral center, but whether is there any cumulene part or biphenyl part or alkylidene cycloalkane part or all these cases. Okay, so this is the way you have to check total number of isomers. So first check structural isomers, then find. Now what happens in geometrical isomer as well? Suppose you have to check geometrical isomer in a particular structure. Okay, so it is having cis and trans. Now in both case, cis as well as trans, you need to check whether cis can show optical activity or not, whether trans is optically active or not. Because if cis is optically inactive but trans form is optically active, then you have to count its enantiomer as well. Clear? Okay, so this is all about how to check this case. Okay, now while calculating stereoisomers, what we actually need to check? We need to check stereoisomers, we need to check geometrical isomers, means cis trans or EZ or syn anti part, right? Now from these you need to check optical isomer part as well. Okay, now here we also need to check active part and meso part. Active part is represented by A and meso part is represented by M. Okay. So this is the total calculation we will be doing here. So first of all, let me introduce a few terminology which is used. Okay. Now what is this stereogenic center or part or area? Simply it is called a stereogenic center, but sometimes we use the term stereogenic part or stereogenic area. Okay. Now what is this? Any part of the molecule or compound which contributes to stereoisomerism is called as stereogenic center or part. Okay. Any part of the molecule which contributes to the stereoisomerism is said to be stereogenic part or center. Clear to you all? Any part of the molecule which contributes to the stereoisomerism. Now how? So that part may show optical activity, that part may be a chiral center, that part may be a cumulene part, okay, that part may be a biphenyl part, maybe a spiro part. So let's see all the cases. Okay. Hope you have noted this definition. Any chiral center stereogenic center or part. Okay, so it will be your stereogenic center. Clear? Now any contributing pi bond. Now what do you mean by contributing pi bond? Means a pi bond which is contributing towards a stereoisomerism. How? It is showing geometrical isomerism simply. Okay. Or through that pi bond it is having stereoisomerism. Maybe due to that pi bond it is making optically active compound. Okay. So you can count this one part, this as one. Now any contributing cumulenes, or shortest if I say allene, that will be counted one part. Now see, sometimes what happens, for any particular cumulene, single cumulene part, I am telling one. Okay, so if you have two parts, contributing parts, then it will be two. Okay. Now contributing biphenyls or pyranes or alkylidene cycloalkanes. Means here I am used cumulenes, biphenyls, pyranes, alkylidene, cycloalkanes. All these four cases have been discussed. What are cumulenes, what are biphenyls, what are alkylidene, cycloalkane and pyranes. These four topics I have already discussed in my previous lectures. How these compounds are drawn, how these structures show geometrical or optical isomers. Okay. So in all these cases you have to count one for each part. Okay. For each part you have to count one. And last, any other part contributing in stereoisomerism, then one. Clear to all? So in this way you calculate the total number of stereogenic center or part or area. Clear to you all? Okay, so students, let's see this with some examples. Find total number of stereogenic center. Okay, okay, so dear students, in these 5 cases let's find total number of stereogenic center. Okay, so first of all in this one, let's see this is a chiral center, so it will be one stereogenic center. From here I can say optical activity. This is also chiral center. I can see this molecule is overall unsymmetrical, right? So it is having 2 stereogenic center. Clear? Now let's see this one. See, this pi bond is in corner, so we are having here CH2. In this corner we have CH2, so it is not contributing in stereoisomerism. Now check this one. This is a chiral center. Okay, now this one, yes, obviously this pi bond is contributing in stereoisomerism. How? It is showing geometrical isomerism. So this is one entire part. See, this is part. Okay, now this is also chiral center. So here you can say number of stereogenic center equals to 3. Clear to you all? Okay, now let's check in this one. See, if I check this one in ring, then this carbon is having this side 2 degree carbon and this side 3 degree carbon, one hydrogen and one methyl. So it is a chiral center. Similarly, this is also a chiral center. So I can say here these 2. Okay, now check this one. In this case, this is a stereo center as it is a chiral center, and this chlorine as well. So here also you are having 2 stereo center. Clear? Now check this one. Okay, I think you have done this. So let's check whether you have done correctly or not, because it is a case where most of the student doubts. Why? Because in this ring, as it is a 6-membered ring, then this pi bond cannot contribute in geometrical isomerism. Okay, remember this thing. Unless you don't have 8-membered ring, there is no GI in the ring due to pi bond. Clear? Now, due to pi bond, yes, you can say that these 2 hydrogens are on same side, so it is a cis form. Definitely you can say this is a cis form, but you cannot make the trans form of it. Why? Because if you have to make the trans form, let me tell you. See, now this part is like this. Okay. Suppose if I make the ring like this, transform. Now from this carbon and this carbon, 4 carbons are already drawn. So using any 2 carbons from this side or this side, I cannot make the ring, 6-membered ring. Okay. So this is the reason why in 6-membered ring there is no cis transform. Okay. So, but this is a chiral center, you can see, because from this carbon, this side is 1, 2, pi bond, 1, 2, 3. Okay, and this here hydrogen and methyl. So it is having one chiral center. Okay, so dear students, in this way you can calculate total number of stereogenic center. Clear? Let me give you 2 more cases. Okay, so find out in this case total how many parts are contributing in stereoisomerism. If I see this is not contributing, why? Because it is in terminal pi bond. Okay, now if I see this one, this part, yes, definitely, and you can see here you are having 3 consecutive pi bonds, so you can say it is planar part. Okay, means it can contribute in geometrical isomerism also, means geometrical as well as that cis and trans form can contribute in optical activity as well. Now let's see total. Yes, we can say this one as a chiral center also. Now this part is also 3 pi bond continue, so this is also one stereo center. And see, this carbon is having chlorine, methyl, ethyl and this different part, so that is a chiral center. So here I can say 1, 2, 3 and 4, so there are total 4 stereo centers. Clear to you all? Stereogenic centers. Now check in this one. Here you can simply see this is a chiral center, this is also chiral center. Now this pi bond is contributing in geometrical isomerism and this pi bond is also contributing in geometrical isomerism, so it's stereoisomerism indirectly. So 1, 2, 3, 4. So here also you are having 4 stereogenic centers. Clear? Done? Okay. Now let's understand what is a stereo center. Now some of you must be thinking stereogenic center. Now I am telling stereo center. Okay, so dear students, you have to understand these two terminologies are very different. Okay, when you say stereogenic center, you take the part which is contributing in stereoisomerism, but when you say stereo center, you count the atom which is contributing in stereoisomerism. Okay, so first of all, let me give the example H, D, T, F. Now in this you can say that this carbon is a stereo center. Okay, why? Because from this carbon atom, if you interchange this hydrogen and fluorine, then you can say that one interchange will give you stereoisomer of this compound. Okay, clear? So from every atom you have to check in this way. Clear? Let me give you another example. See, as you know, this is cis 2 butene. Okay, now in cis 2 butene, if I see, let me make the numbering 1, 2, 3, 4. Okay, now 4 carbon atoms you have. Interchange across C2. Now across C2 carbon, if I interchange both the groups, what I will get? I will get HMe as it is, but here I will get methyl this side and hydrogen this side. See, this you have made transform. Okay, so you can see on interchanging through this carbon atom C2, you can get its stereoisomer GI obviously. Now again, let me interchange across C3 and what I will get? This HMe as it is. Okay, this Me and H. Now you can see this is also transform. Okay, so on interchanging through C2 or C3, in both the cases I am getting its stereoisomer. So dear students, stereo center defines for a particular atom through which any interchange of two groups can give its stereoisomer. Clear? So let me give you the definition. Now, dear students, when I say stereo center, I simply means any atom in a molecule. So, in a given molecule, I am telling about any atom at which interchange of any two groups or atoms. So, when you interchange any two groups or atoms from any particular atom, interchanging the two groups or two atoms, if you get its stereoisomer, then such atom is called as a stereo center. Okay. Now let's take a few examples. Now in these two cases, you have to find out the number of stereo centers. Okay. Done? Okay. See, this is a chiral center, so it is also a stereo center. This is also chiral center, so stereo center. Now, as this pi bond is contributing in geometrical isomerism, cis and trans, so this carbon atom and this carbon atom both will be counted as a stereo center. See, if I have to tell this whole part, then it is a stereogenic center. But if I have to say stereo center, I mean this carbon atom is also a stereo center and this is also a stereo center. Why? Because if I interchange, here you are having hydrogen and this group. So if I interchange this hydrogen and this group, so from this part interchanging or this part interchanging, on both cases I can make its cis and trans forms. Clear? Now, similarly, this pi bond is contributing, so this atom and this atom. So dear students, you can see from this part, both carbon atoms, here also both, 2 plus 2, 4, 5 and 6. So here you are having 6 stereo centers, okay. Now let's check this one. See, this is a chiral center. How? This carbon is having methyl, ethyl, hydrogen and this part, okay. Now this pi bond is contributing in geometrical isomerism. So both the carbons from this side and this side. So here you are having 3 stereo centers. Clear to you all? Okay. Now in the same question, let me ask you, as I have already discussed about stereogenic center. So here if I say stereogenic center, then stereogenic center in first will be 1, 2, this part is 3 and this part is 4. Okay, 4. Clear? Now check this one. Stereogenic center, here 1 this chiral center and this part, only 2. Clear? So dear students, I think you must be clear about stereogenic center and stereo center. Now let's see the calculation part, how to check total number of stereoisomers. calculation of total number of stereoisomers. Okay. See, case 1 I am taking when compound is unsymmetrical. Okay. In another way, I can also say when numbering can be done from one side only. See, the compound must be unsymmetrical. Okay. And in another way I am telling, since if you suppose you have an open chain compound, you can make numbering from this side or this side, both possible, means definitely it is symmetrical type, it is not unsymmetrical type. Okay, so numbering must be done from any one of the side only. In such a case, you have to say total number of stereoisomers equals to 2 to the power n. 2 to the power n. Okay. Now, what does this n represents? In simple terms, if I say, then this n represents number of chiral center or number of contributing parts, or simply in one way, stereogenic center. Okay. This n represents number of stereogenic parts or center. Clear? Means that contributing allenes, contributing cumulines, contributing biphenyls part, contributing double bond, pi bond, contributing chiral centers. So all those are involved here. Clear to you? In one word, n equals to number of stereogenic center or part. Clear? That's why I used earlier the term n, stereogenic part or stereogenic center. See, I am not using stereo center here, that is different. Okay, that is just to tell you what is stereo center, stereogenic center. Clear? Now, in simple terms, you can write n equals to number of chiral center plus number of contributing pi bonds in stereoisomerism plus number of contributing allenes, biphenyls, any other part. Clear? So you can say n equals to number of chiral center plus number of contributing pi bonds in Si plus number of contributing allenes, biphenyls or any other part. Any other part may be alkylidines, cycloalkanes, spiranes, spirocompounds, cumulines, and any other case, any other part. Okay, clear? Now dear students, see, in sometimes you may come across a formula of total number of optical isomers equals to 2 to the power n, 2 to the power n. So when you say total number of optical isomers 2 to the power n and total number of stereoisomers 2 to the power n for same, it simply means there is not at all any case of geometrical isomerism. Okay, so sometimes this formula is also used for total number of optical isomers. Clear? Okay. Okay, so dear students, here you have to check total number of stereoisomers. Okay, let's see. See, in this case I can make numbering from one side only, because 1 bromo and 2 chloro is better than saying 1 chloro and 2 bromo. Alphabetically bromine is preferred because the location of substituent is fixed, 1 and 2. Okay, so 1 bromo 2 chloro cyclohexane. Here total number of stereoisomers is 2 to the power 2 equals to 4. See, what are the 4 cases? When both are on wedge, then it is optically active, so its mirror image, both on dash, and one on wedge and another on dash, that is active, so its mirror image. So all 4 cases. See, if I have to use here the formula total number of optical isomers equals to 2 to the power n, 2 to the power 2, that is also correct. Why? Because there is no case of meso part here. Okay, now if I will say whether I counted the geometrical part or not, yes, I have already counted. When I said that 2 in wedge, when both on same sides and both on opposite sides, means both bromine on same side, either wedge or dash. As I told, both wedge, then also optically active, so its mirror image, both dash, then also active. Now when on wedge and this one on dash, then it is active. Okay, transform, then also its mirror image. So I have counted the cis trans part also. Now check this one. In this case, this is a chiral center. Okay, now this part is a stereogenic part. Why? Because it is showing geometrical isomerism. Simply if I have to say 2 to the power 2, why 2 parts? How? Simply cis R, cis S, trans R, trans S, all 4 cases I have told you. Okay, now check this one. This is a chiral center, this is also chiral center, and this part is also involved. Okay, clear? So simply if I have to check, I can say 2 to the power 3 means total 8 stereoisomers will be possible for this compound. Okay, now check this one. See, this is a case where you can make numbering from this side only. Okay, now here what I can see, there is no chiral center, but yes, this pi bond is showing geometrical isomerism and this pi bond is also showing geometrical isomerism. Clear? So what are the possible cases? Cis, 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 trans. And now when this will be trans, then this will be cis. Okay, and trans, trans. Clear? So there are 4 cases. Both cis, both trans, this one cis, this one trans, or this one trans, this one cis. Clear? So there are 4 different cases. Okay, done. So dear students, now let me take you to different examples. Case 2. Okay, now what is case 2? When the compound is symmetrical. Symmetrical in the sense it can be numbered from both the sides. Okay, numbering can be done from both sides. Okay, now if you say how it can be done in open chain or how it can be done in ring, so let me give you 2 examples here. First example is, see, from here also 1,2-dimethyl cyclohexane, or from here also 1,2-dimethyl cyclohexane. So from this carbon or this carbon, and both are chiral centers, right? Second, this example. Okay, here also you can make numbering from upside or from downside, no issues. 2 chiral centers you are having. Clear? So in this way, numbering can be done from both sides. Or you can see here, this is a meso compound as per this particular structure or this isomer. Okay. If I interchange one of the hydrogen and chlorine, it will become optically active. Here also, if you make this both methyl on wedge or both methyl on dash, then it will be a meso. But if I make one on wedge and one on dash, means transform, then it will become optically active. Clear? Now let me tell you how to check by formula. Here also we use the term N, number of stereogenic parts, but the formula is variable, different. When N is even, see, we use the term N, okay, number of stereogenic part. But now what happens, suppose N is your number of stereogenic part which is even number, means just like here 2, here also 2. So what you will do, then you can say number of active A, as I used earlier, optically active equals to 2 to the power n minus 1, and number of meso M equals to 2 to the power p minus 1, where p equals to n by 2. Okay, as n is even, so even number by 2, it will give you an integer value only, positive integer value. Okay, 1, 2 or 3 or so on, whatever. Suppose n equals to 2, then 2 by 2 is 1, n equals to 4, then 4 by 2 is 2, simply. Okay, so active isomers is given by 2 to the power n, and meso part is given by 2 to the power p minus 1. Clear? Now using this formula, you have to calculate total number of stereoisomers. Again I am telling, the term is used is total number of optical isomers. Why it can be used? Because if the compound is not showing geometrical, then you can check only optical part. Or in another way, when you calculate the total number of optical parts, then by default geometrical parts will be counted. Now let me tell you how. See, let me calculate in these two examples only. As you are having here n equals to 2. Okay, so as you have two chiral centers, so n is even, numbering can be done from both sides. So active is given by 2 to the power 2 minus 1. 2 minus 1 is 1. 2 to the power 1 is 2. So here active equals to, and meso equals to 1. Clear? So students, as per calculation, now as per calculation, active is 2 and meso is 1. Now let me check theoretically. See, I can make both on wedge. Suppose both methyl on wedge, then it is trans, and one on wedge and one on dash, it is cis. So I made its a geometrical part, both wedge and one wedge, one dash. Now let me check cis form. When both on wedge, it is optically inactive. So it is actually meso part. Done. Now when one wedge and one dash, no POS, no COS, then it is optically active. So its mirror image will also be there. So two parts optically active, total 3. Now while counting total 3, we have by default counted the geometrical part as well. Okay. So cis trans, you can say it will be having cis and trans. Active 2 and meso 1. Clear to you? And total, if I have to say, it will be 3 total isomers. Okay, done. Now check this one. Similarly, same formula here. Active is 2 and meso is 1. How? When both Cl on same side, it is a meso. So no need of taking its mirror image. But when one Cl and H is rotated, then you can say it will become optically active. So its mirror image will also be taken. Clear? Okay. So I think everyone must have understood this formula, right? See, we will not go in detail using the formula always, right? don't worry about remembering this formula, because most of the cases what happens, without using the formula you can check by using this thought, okay, by imagination, cis part, trans part, which part will be active, which part will be inactive, all such cases, okay. When n is odd, now let's see what happens when n is odd, okay. Number of optically active part means A and meso part M. See here, meso part is again given by 2 to the power p minus 1, but here p will be n plus 1 by 2. Why? Because n is odd. Suppose n equals to 3, 5, 7, then 3 plus 1, 4 by 2 is 2. That's why we have to take n plus 1 by 2. Or you may say this as 2 to the power, p is n plus 1 by 2 minus 1. So it is simply n minus 1 by 2. Okay. Now remember this one, very similar. There also p minus 1, here also p minus 1. But p, value of p changes. And active is given by 2 to the power n minus 1 minus 2 to the power p minus 1. Because in this case, when you take 2 to the power n minus 1, you by default calculate the meso part also there. Okay, I'll tell by using the example. So, total means active plus meso is given by 2 to the power n minus 1. Okay, so dear students, earlier what we find earlier when n is even, total equals to a plus m equals to 2 to the power n minus 1 plus 2 to the power p minus 1. But here active equals to 2 to the power n minus 1 minus 2 to the power p minus 1 and meso 2 to the power p minus 1. So on totaling, I can say active plus meso equals to 2 to the power n minus 1. Clear to you all? Let's see using the examples. Find total number of active plus meso in given compounds. Okay, so first case, okay, so here you have to find out total number of stereoisomers, or I am telling total number of optically active parts and meso parts in the given compounds. Okay, so dear students, first of all you find out, then match with my answer. Okay, so no cheating. I think you must be doing by yourself first of all, right? Don't see the answer first. Okay, so let's see. See, in this one, if I have to make numbering 1, 2, 3, 4, 5, 6, numbering can be done from both sides? No, only one side. It is unsymmetrical. There are 4 chiral centers, carbon number 2, 3, 4 and 5, but there are no meso part. So simply I can say by observation meso 0, and active or total number of stereoisomer 2 to the power n 16. Clear? Okay. Check this one. Yes, here actually it is tartaric acid. You remember tartaric acid? So in tartaric acid, as you know, it can be numbered from both the sides. So already you are having 2 chiral centers, but here n is even. So active equals to 2 to the power, active is 2 and meso is 1. How? If both OH on same side, then you can say that it is meso, and if one OH on this side, another OH on this side, then it will be active, so its mirror image will also be taken. So 2 active, 1 meso, total here 3. So here you cannot use the term 2 to the power n. 2 to the power 4 will be giving the mirror image of meso part, which is not stereo, which is actually identical. Okay, so that one case is left here. Okay, now see here, simple use 2 to the power n. Here you can just imagine the 3 cases. One is meso, one is active, its mirror image. Now let's check this one. Yes, in this case what happens, you can make numbering from both the sides, from upside or downside, that is okay. 1, 2, 3, 4, 5. So this is suppose 1, 2, 3, 4 and 5. So you are having 3 chiral centers, but you remember the concept of pseudo chiral center. So in such cases, when the compound is symmetrical type and numbering can be done from both sides and you are having odd number of chiral centers, then there must be a case of pseudo chiral center. As I told you earlier, you have to count the pseudo chiral center as a chiral center. So here stereogenic center or chiral center equals to 3. Now using the formula of active, first of all let me find meso. Meso is 2 to the power p minus 1. Here p is n plus 1 by 2. N 3. 3 plus 1 by 2 is 2. So p equals to n plus 1 by 2. 3 plus 1, 4 by 2. Okay, so p is 2. M equals to 2 to the power p minus 1. So 2 meso. Clear? Now active equals to 2 to the power n minus 1 minus meso, means 2 to the power 3 minus 1, 2, 2 to the power 2, 4 minus 2 is 2. So here active equals to 2. So 2 active and 2 meso. Total can be find out using the formula 2 to the power n minus 1. Total 2 to the power n minus 1 for this question. Okay, so n is 3, 3 minus 1 is 2 equals to, you can say 4 total, and you can see here meso 2, active 2, 4 cases only. See guys, if you have to check using 2 to the power n, you will be getting 2 to the power 3, that is total 8, but here actually it is 4. So there are 4 cases which you have rejected. Now let me tell you what are those possible 4 cases which has been rejected. Okay, see, this is a meso, so its mirror image is rejected. Now if I rotate this H and Cl from C3, then that will also give meso, but its mirror image will be rejected. Clear? So I have told you 2 meso cases and both its mirror image are rejected. So 2 meso is done. Now let me do one active part. If I rotate this H and Cl across C2, then it will become optically active part. So its mirror image will be there. So 2 active part is there. Now what you can think, sir, why don't you rotate across C4? Means just interchange this H and Cl across C4. So either you change across C2 or C4, that is same, because you know the properties of Fisher formula that on rotating, suppose this is a Fisher having 3 chiral centers. So if I just interchange in the plane of paper across 180 degree, so I will get the identical compound. So here also that is the case. You can draw by yourself in the notes and check it. Okay, case 1, just interchange across C2. Case 2, interchange across C4 and check both cases are same or not. Okay, so here interchange across C2 and you get active, its mirror image. So 2 active, 2 meso, total 4. Clear? Okay. Okay, so this is a question. In this question you have to find out the total number of stereoisomers. Find out by yourself first. Okay, done. Okay, this part is a cumulene part and it is a contributing part. Also this part can show geometrical isomerism. This is a chiral center, this is a chiral center, this part is showing GI. Okay, so if I say total number of stereogenic center 1 2 3 4, simply total number of stereoisomers 2 to the power 4, I can get 16. Clear to you all? So total number of stereoisomers here 16. Okay, simple, because you can make numbering from one side only. If you have to find out total number of stereoisomers, total number of stereoisomers in glucose, second, okay, find out in two cases. See, if I say glucose, we have discussed this compound in epimers and anomers topic in my previous lectures. Okay, so you remember across C3 you have to make OH on left side. Now you can see in this case 1 2 3 4, you are having 4 chiral centers, and all the 4 chiral centers, it is unsymmetrical type, right? So simply 2 to the power 4, you get 16. Total number of stereoisomers across glucose will be 16. Now check this one. In this case simply you are having 3 chiral centers. Okay, so simply 2 to the power 3, you get 8. Total stereoisomers here 8. Done. Okay, so dear students, here we discussed about how to check total number of isomers, how many are optically active, how many will be optically inactive, how to check the meso compounds. Okay, and we have discussed about stereo center and stereogenic center. So check all the examples properly, and we will continue our next lecture with the same, using different type of calculations, interconversions, and how to check different forms. Okay, we'll continue in our next lecture. Okay.